tell that the term cantilever actually originated as a construction technique used by James Eads to build his great arch bridge over the Mississippi River at St. Louis. To refresh your memory, let me show you what that technique looked like. During construction, Eads supported the incomplete arches from either end of the span using temporary stay cables that were attached to temporary towers out here at the ends of the span, like this. As each new segment of the arch was added during construction, it was attached to the end of the existing construction, and then new stay cables were added in order to tie the arch back to the temporary support structure, thereby allowing the structure to be completed without the use of temporary centering as we saw in other types of arch structures. Eads referred to this manner of construction as the canted lever, and the name stuck. In this case, canted is referring to the inclination or tilt of the incomplete construction. Over time, the term cantilever was then applied to any structural element with one unsupported end, as you see here. The cantilever truss, then, is just one variation on this theme. Let's see how that works. First, we'll get our cantilever construction out of the way. And now let's build a cantilever truss. Now, the most common configuration for cantilever bridges is one that has 4 supports. 2 exterior supports, as shown here, these are called abutments, and then 2 interior supports, or intermediate supports, which are called piers. Before we actually build the cantilever bridge, though, let me show you what the 2 alternative truss configurations that could also be used to span this gap would look like. The first alternative would be to actually span the entire distance with 3 independent simply supported spans. This would be the equivalent of the Tay bridge that we just saw. So we might place these short, simply supported spans out here on the ends, and then a longer simple span between the 2 intermediate supports. The key characteristic of this system, of course, is that all 3 spans are essentially independent of each other, and they're all simply supported. This is an advantageous system because it's easy to design. The problem is that it's not really structurally efficient enough for very long spans. And the span that we're talking about here at the Firth of Forth is on the order of 1,700 feet. A simply supported span simply wouldn't have worked. An alternative, then, would be the continuous span. So let's replace our simply supported trusses with a continuous truss. This now is one single structure that spans from one abutment all the way out to the other, passing over the 2 intermediate supports. The continuous span is far more structurally efficient than the series of simply supported spans. It's structurally efficient for exactly the same reasons that a continuous beam was more efficient than a series of simply supported beams. We talked about that back in our lesson on beams. The continuous bridge is efficient because, as a result of these intermediate supports, it tends to bend concave downward over the supports, concave upward in the center, and that balancing of moments between positive and negative turns out to be significantly more efficient. The problem is that this bridge is very difficult to design and analyze, and that would have been particularly important in the era that we're talking about, which was really the dawn of the era of science-based design, when computational tools were still relatively primitive. And so designing a structure of this complexity, resulting from its continuity, would have been an extreme challenge. The other problem with the continuous truss configuration is that it's highly vulnerable to problems with expansion, contraction, and support settlement. Let's say that this support here dropped a few inches, or that the bridge dropped with respect to that support. The movement of a support underneath a continuous bridge will cause the bridge itself to bend, and therefore we could see significant stresses being developed in the structure even before any loads are applied. And that is potentially problematic and would have been a reason why engineers of the era would have been reluctant to use the continuous bridge. Now, with those 2 structural configurations as points of comparison, let's look at the cantilever. To build our cantilever bridge, we're going to start by putting 2 spans out on the ends. One here and one on the opposite side. Each of these end spans actually is typically referred to in terms of two components. The component out here on the outside is called the anchor arm, and the component on the inside is called the cantilever arm. And indeed, this is the reason why the bridge configuration is called a cantilever. It is the fact that the cantilever arm of the end span is indeed unsupported. Now, in a moment, I'm going to complete the structure by putting what's called a suspended span right here in the center. But I think you can see, now that you've developed a fine appreciation for the principle of equilibrium, that as soon as I hang a span out here in the middle, the whole structure is going to tip over and fall into the middle of the river. So an integral aspect of the design of a cantilever bridge is that it requires some sort of counterweight out here on the anchor spans. They need to be anchored to the abutments in order to counterbalance the additional weight that we're about to add with our suspended span. So here is our suspended span, and the other critical characteristic of the cantilever that you need to recognize as I'm attaching it is that the attachment between the suspended span and the cantilever arms of the end spans is done entirely with this pair of pinned connections. And so what we really have in the center span is, for all intents and purposes, a simply supported truss. That's really important because that principal limitation of the continuous bridge, that is, its susceptibility to additional stresses caused by support settlements, simply isn't an issue with a cantilever. Note that if this support moves, the bridge is articulated, so it's able to accommodate that movement without any difficulty at all as a result of the two hinges that exist in the middle of the span. And while it does have this favorable quality, it still has essentially the same level of structural efficiency as the continuous bridge does, because it still has that characteristic of bending in negative curvature over the supports and in positive curvature out near the center of the span.